In the previous class, we discussed about the synchronous SRAM and synchronous SRAM. In that synchronous SRAM, we already discussed flow through SRAM. Okay, what is the use of flow through SRAM? Here, this is the flow through SRAM. Next one is pipelined SRAM. Here, in this flow through SRAM, it includes the registers on the inputs but not on the data outputs. Just remember this. Okay? See here. Is it audible? Hello? Is it audible?
Yes, sir.
Yeah, okay. See here, this flow through SRAM, this is a synchronous SRAM. Okay, just remember here, it includes registers on the inputs but not on the data outputs. Okay, then why it's called flow through? That means the term flow through refers to the fact that data read from memory cells flows through directly to the data outputs. Okay, that remember why it's called the flow through. Directly when we are doing the read operation, okay, the data directly is sent to the flow through the data outputs. There is no multiplexer, there is no tri-state devices and all. Okay, directly the read data will send it to the flow it to the data outputs. Okay, and just go through this timing diagram for the how this flow through SRAM will operate, which can perform the read and write operation. Okay, just go through these signals: clock, address, enable, WR, write. When it is WR signal is high, which performs the write signal. When it is low, which performs the read operation. Okay, here D in, data is ready to write, which is the preparation for write operation. Okay, at A1 register address. At A1 register data, and when the WR signal is high, enable signal is high, then which is ready to at clock 1, at clock 1 signal, which is ready to do the write operation. Data is ready for write operation. Okay, here at MA2 during clock 3, what will happen? In clock 2, which is ready at the end of clock 2, which is ready for read operation. That means at address A2. Okay, just go through this diagram, timing diagram. Next one is pipelined SSRAM. Pipelined SSRAM. Here we already know that in flow through SSRAM, at the input side we have the registers. At the output side there is no registers. But here the pipelined SSRAM, which includes a register on the data output as well as register on the inputs. Both sides, at the input side also we have the registers, at the output side also we have the register. Okay, a pipelined SSRAM is useful in higher speed systems where the access times of the memory is significant proportional of the clock cycle time. When the access time is less, that means we perform the higher speed. It means access times means which can access the data as soon as possible. Okay, a pipeline SSRAM is useful in higher speed systems where the access times of the memory is significant proportion of the clock cycle time. If there is no time in which to perform combinational operation on the read data before the next clock cycle ends, it needs to be stored in an output register and used in the subsequent clock cycle. Just remember here, if there is no time in which to perform combinational operations on the read data before the next clock ends, it needs to be stored in an output register before the read operation, which can be stored in the output register and used in the subsequent clock cycle. A pipeline ssram provides that output register. How do we know that? Okay, the timing for the inputs is the same as that for a flow through ssram. The timing diagram for pipelined ssram is same as the flow through ssram. The difference is that the data output does not reflect the result of a read or write operation until one clock cycle later. Okay, immediately after the clock edge, marking the beginning of that cycle. See here how the timing diagram of this one I will show you here. Yes, so the block diagram of pipeline ssram. See here, the particular one clock cycle, there is a particular one clock cycle, the operation will complete. See here, they mentioned here. A pipeline ssram provides that output register. The timing for pipeline ssram is same as that for a flow through ssram, except that the data output does not reflect the result of a read or write operation until one clock cycle later. Immediately after the clock ends, marking the beginning of that cycle. Up to the complete of one cycle, the next process will not process. Okay, except that the data output does not reflect the result of a read or operation until one clock cycle. For one clock cycle, one operation, either it's read or write. Check it here. See here, and here, and here. One clock cycle, and another one. This is one clock cycle. A1 address, A2 address. Okay, here this is enable here. At A1 which performs the write operation, at A2 which performs the read operation. Access is right. Next topic is dynamic RAM. Dynamic random access memory. There are two types of random access memory: RAM, static RAM, and dynamic RAM. We already discussed static RAM. There are two types of static RAM: asynchronous and synchronous. Okay. Then synchronous can be classified as flow through ssram, and one more is pipelined ssram. Just go through that. Next we go for the dynamic RAM. Here DRAM, this is the schematic diagram of dynamic RAM, which consists of the capacitor for the purpose of charging and discharging. Okay. Then here we have the transistor, MOSFET, NMOS transistor. Okay. Here the gate terminal is connected to word line. and bit line is connected to either source or drain terminal. The transistor which has three terminals: gate, drain, and source. Gate, source, and drain. At the source side, we apply the inputs. Okay, word line is also high. When it is high, what will happen? The capacitor will be charged. Okay, the charging means here the data 1 is stored. Discharging means data 0 is stored. Okay, just remember here. DRAM is another form of volatile memory. Volatile means if the power supply is there, okay, that device, that memory will on. It can do the storage operation. Okay, DRAM is another form of volatile memory that uses a different form of storage cell for storing data. For storing data. SRAM uses storage cells that are similar to D latches. Storage cell for dynamic RAM uses a single capacitor and a single transistor. Here the SRAM, you can construct SRAM using 6 transistors. The number of transistors are more. Then the area which requires is also more. But here the dynamic RAM, which requires only 2 components, single capacitor and a single transistor. This is the schematic diagram of that schematic diagram of DRAM. DRAM cells are much smaller than SRAM cells, but access times of DRAMs are longer than that of the SRAMs. Which is faster here? SRAM is faster than DRAM because here the access times of the DRAM is more, longer than the that of the SRAMs. Okay. DRAMs are more commonly used as a, wait a minute. Okay, we'll leave it. DRAMs are more commonly used as a main memory in computer systems since they satisfy the need for high capacity with relatively low cost. Why it's low cost? Which requires only 2 components. That's why which can be used as main memory in the computer systems. The choice between SRAM and DRAM depends on the requirements and constants of each applications. The choices for SRAM and DRAM, which can depends on requirements and constants of each applications. DRAM represent stored 1 or 0 bit in a cell by the presence or absence of charge on the capacitor. When the capacitor charged, data 1 is stored. When it is discharged, data 0 is stored. Just remember that. To write to the cell, the SRAM, to add to the cell, the DRAM control circuit pulls the bit line high or low and turns on the transistor, thus charging and discharging the capacitor. To do the right operation, okay, this transistor should be on. When it is on, when this gate terminal is high. You know that when the input to the NMOS transistor is high, then which is on condition, which is in the on condition. That's why to do the right operation, the white line should be high. Okay, here you can send either 0 or 1 through the bit line. During the right operation, when you wanted to store the 1, logic 1, the capacitor is charged. Okay, during the when we can do the write operation of 0, this capacitor will be discharged. They mentioned here to write to the cell, the DRAM control circuit pulls the bit line high or low. Bit line means this is the bit line. Okay, here you can set to either 1 or 0. Bit line high or low and turns on the transistor, thus charging and discharging the capacitor. Okay, then to read from the cell, the DRAM control circuit pre-charges the bit line to an intermediate level, then turns on the transistor. To do the read operation, the control circuit, DRAM control circuit, pre-charges the bit line to an intermediate level, then turns on the transistor. Okay, here can do the, when you can perform the read operation, this bit line should be at pre-charge. Pre-charge means it is at high. It is at high. If it is 1, okay, if it is 1 means what will happen? There is no, this is on, word line is on. Okay, if you store the capacitor charged, that means the data 1 is stored here and bit line is charged here. Then what will happen when the word line is on? There is no discharge take place. Okay, it is at 1 only. Here also 1, here also 1, both sides. Here also 1, here also 1. I will show you here. Here 1, this is at VDD. That means VDD means it's at 1 only. When this is on means, okay, there is no discharge take place. Then we say that it's remain at 1 only. Bit line is remain at 1 only. Then we say that the stored data is 1. If data 0 is stored here, the data 0 is stored here and bit line is at pre-charge, that means VDD, then word line is on, what will happen? There is discharge will take place. Discharge will take place. Then we say that bit line which can read the data as 0. Just remember this, the read operation and write operation. Okay. Then a sensor detects and amplifies the change, okay, thus determining whether the cell stored a 1 or a 0. This destroys the stored value in a cell, so the control circuit must restore the value by pulling the bit line high or low before turning off the transistor. Sometimes what will happen here, when the data is stored either 1 or 0, okay, the data is destroyed. If it is 5 volt means it will not complete, that stored data is not 5 because of some leakage. What will happen? The data will be destroyed. This destroys the stored value in a cell, so the control circuit must restore the value by pulling the bit line high or low before turning off the transistor, okay, because of some leakage. Okay, since the time taken to complete the restoration is added to the excess time, the read cycle is significantly longer than that of a SRAM. Here must and should you can restore the data during the read operation. During the read operation. Is it audible? Hello?
Yes, sir.
क्या चल रहे?
हाँ रे.
हाँ. Here, during the read operation, we can do the restore the data. Okay, just remember that. That's why access time is longer than the SRAM. Next topic is multi-port memories. Multi-port memories. A single port memory will have just one port for writing and reading data. It has only one address input. Thus, a single port memory can perform only one access, either a write or a read operation at a time. Okay, single port memory which can do the single write and read operation. Okay, a multi-port memory has multiple address inputs with corresponding data inputs and outputs. It can perform as many operations concurrently as there are address inputs. Multi-port memory, which can do the more number of the operation, perform many operations. Okay, multi-port. The most common form of multi-port memory is a dual port memory. See here, this is the symbol of dual port ssram. A1, A2, D in 1, D in 2, D out 1, D out 2, enable 1, read REN, okay, enable 2, WR1, WR2, clock 1, clock 2. Dual address lines, dual input lines, dual output lines, okay, enable signal and write signal and clock signal. Two clocks, okay, dual, that means two. That's why dual port memory. A multi-port memory can perform two operations concurrently. A multi-port consumes more circuit area than a single port memory with the same number of bits of storage, since it has separate address, decoders, and data multiplexers for each access port. Only the internal storage cells of the memory are shared between the multiple ports. Okay, because of the multi ports, what will happen? The area of the circuit becomes more. The only difficulty is the case of both subsystems accessing the same memory location at the same time. Just remember here, we have two ports. Okay, we have two ports. If both the subsystems accessing the same memory location, for example 001 and so somewhere 001, which can accessing the same memory location at the same time, that is the difficulty. If both access are reads, they can proceed. If one or both is a write, okay, the effect depends on the characteristics of the particular dual port memory. In an asynchronous dual port memory, a write operation performed concurrently with a read of the same location will result in the return data being reflected. On the read port, after some delay, okay, two write operation performed concurrently to the same location result in an unpredictable value being stored. These are the some difficulties. Okay, asynchronous dual port, and one more is synchronous dual port memory. In case of a synchronous dual port memory, the effect of concurrent write operation depends on when the operations are performed internally by the memory. Here, this is the Verilog model of a dual port 4K into 16-bit flow through ssram. One port allows data to be written and read, while the other port only allows data to be read. Okay, one port which can do the read and write operation. Okay, one port which can allows only the data to be read. Okay, just remember, we know the structure of Verilog module. Okay, module, dual port ssram, the module name. Okay, the input components are output register 15 is to 0, D out 1. Okay, here the output is how many bits? 16 bit. That's why 16 bit. Then 4K. 4K means 4000 address lines. How many address lines? 4000. For 4000, here we have what is the memory address bits? How much? Log of 4000 divided by log of see here, output bits is 16, input bit is also 16, D out 1, D in 1. Okay, then address. Here 4000 address location means log of 4000 with base 2 divided by log of 2. You can see here, log of 4000 divided by log of 2 can perform. Okay, using that equation, we will get the number address bits. Here, the 12 address bits. I will show you here. What is the log of 4000 divided by log of 2? It's 12. Okay. Log of 4000 divided by log of 2. That means, wait a minute, I will show you. You can leave it. Yeah, okay. Check it, where is log of log signal here? Okay, leave it. Log of 4000 divided by log of 2 is 12. Okay, that means it indicates the number of address bits. That means 11 is to 0 address lines A1. And enable 1 and WR1. These are the outputs. See here, just refer this symbol. Wait a minute, some problem in here. See here, these are the inputs. A1, D in 1, A2, D in 2, enable 1, WR1, WR2, REN2. These are the inputs. Output are D out 1 and D out 2. D out 1, 16 bit, D out 2, 16 bit. Inputs also 16 bit, D in 1 and D in 2. A1 and A2, these are 12 bits. Just remember that. say D out 1, see D out 2, this output register we used. Okay, then A2 is also 12 bit. Enable 2, that is also 12 bits. Okay, input clock. Okay, then this is within the bracket, and here also within the bracket put the semicolon here. Then register 15 is to 0, data RAM, register 15 is to 0, data RAM 0 is to 4095. 0 is to 4K means 4096. 0 is to 4095. Always at the end, positive edge clock. Okay, if enable equal to 1, which performs the write operation beginning at the beginning, data RAM A1, okay, that is equal to D in 1. Here A1 means address bit, address A1, D in 1, then D out 1 is equal to D in 1 only. Okay, here which indicates the address location. For each address location, data is stored. For example, 000, at that location, the output the data is stored. That is write operation. Okay, at the output side also, D in 1 only. And for the if operation, else if it is not equal to 0, the D out 1 is which can hold data RAM, whatever the address location here. That is for the A1 address. Okay, during here we did write operation and also read operation. Okay, read and write, this is write operation completely, this is read operation. Just remember here, I'll write it here. This is write operation. Write operation, this is read operation. Just remember this. Write and read. Write and read operation. Okay. Then next one. See here, we already discussed that. Which can in one port which can perform the read and write operation both. One port which can perform only the read operation. Just remember that dual port memory, in that one port which can completely perform read and write operation, which can perform completely read and write operation, and another port which can perform only the read operation. That's why here one port, okay, with A1 address D in 1 and D out 1, okay, is the output, D in 1 is the input. Okay, this is port 1, this is for port 1. Port 2, always at positing your next clock edge, if enable equal to 2, D out less than equal to data RAM A2. Only this is read operation. This is the read operation. This is the read operation. Just remember that. Here, this is for read operation. Okay. And this is for write operation. Write and read both. This is about the multi-port memories. Just remember that, which has the multiple ports. Which has multiple ports. Okay. For example, this is the block diagram of dual port ssram. Okay. In the dual port ssram, one port, this is this side. One port will perform the read and write operation both. Okay. Here, one port will perform only the read operation. I hope it's clear. Okay, go through this program also. I will send these notes in Google Classroom. Please go through that. Okay, please refer the Google Classroom and all of you join it. Any doubts? Any doubts? Asya, hello, Akshata, all of you unmute. Hello.